Thanks for the introduction. And first of all, I'm sorry for the slides. Like it seems to be a little bit messed up, and I hope it's okay. So I'll talk about hardness amplification, and this is a drawing work with my advisor, Prashant. So for many problems, we tend to believe that there is no efficient algorithm can solve the problem in the worst case. So in particular, it means that for any efficient algorithm A, there must exist some kind of inputs such that on which the algorithm cannot solve on it. So a certain example is like if we believe P log equals NP, that means for NP language, there is no polynomial time algorithm can solve the problem in worst case. So correspondingly, if we have this algorithm that is called the worst case algorithm, sometimes it might be hard to directly obtain a worst case algorithm. So people may think about some kind of relaxation about that. For example, the average case algorithm. If we know the input distribution of the like over X, and then we allow the algorithm to only wins on a large fraction of the inputs, for example, 0.99, then correspondingly, I refer to, like, by taking the negation of this problem, it would refer to a mild average case hardness. That means for any algorithm, the efficient algorithm, it cannot solve the problem for larger than 0.99% of the input. So, but this kind of hardness may not that sufficient for the purpose of cryptographic primitives design. So ideally, we want this kind of stronger hardness, which is say like for any efficient algorithm A, it cannot obtain a significant advantage for for solving the problem pi. You may notice that there are some kind of gap between this different level of hardness. In order to bridge them, we have some techniques. For example, the worst case to average reduction. That means if we can solve a problem in average case, then it may be okay to obtain a worst case algorithm. And for the different level of average case hardness, and this is a technique called hardness amplification. If we are able to bridge the gap between these different words, then it seems to reach a very good stage, a stage of win-win. That means either we can have the average case algorithm that wins on a large fraction of the inputs, or we can have a strong average case hardness. Then we may be able to have the construction of cryptography. And besides of this reason, it is also an interesting thing to study because this is an inherent property of a problem itself, that whether there exists a self-reduction or self-amplification. We define the average case hardness usually with respect to a problem and a distribution on the output domain. So we call that a function f is a delta hard on the distribution D for some circuit size. If for any circuit C within the size S, the probability that C agree with F is bounded by delta. So let's try to understand how this delta implies the hardness. Intuitively, a smaller delta may imply a stronger hardness because this is a stronger condition. And there is a strict lower bound for the strongest hardness we could imagine, because there is always a trivial algorithm that I randomly select an element from the output domain and then just output it. And this algorithm, regardless of the input, it will always wins with probability 1 over the size of sigma. So, with this notation, we can define what is hardness amplification. So starting with the assumption that f is 1 minus delta hard, this delta may be a constant or inverse polynomial on a certain distribution D for circuit size of S. We want to obtain a statement like there is another function f prime. It is delta prime hard, and delta prime is a small value. Maybe another distribution D prime for circuit size of S prime. So in the following, we may omit the distribution D and D prime if it's clear from the context, and also omit S and S prime if they don't differ too much. For example, just a inverse polynomial factor, and then it should be fine. Okay, A common approach for doing hardness amplification is by taking multiple copies of the function f, and then use a function g to combine it together, construct another function f prime. So if we take the g to be the identity function, then this is the direct product lemma. So just for intuition, if you sample multiple copies of xi's and try to calculate fxi, then with high probability, this xi should hit a very hard instance, so making the the problem much harder to solve. If you take the function g to be the parity function, and then this is the Yalsa-Exel lemma, and it works for the decision problem, which the output is restricted to 2 values, and then the hardness can be amplified from 1 minus inverse polynomial to some half plus inverse polynomial hardness. Okay. There are also some other works, like for example, for the NP problems, by taking the function g to be the monotone function. So then one question maybe asked is like, why we cannot use Yalsa-Exel lemma to amplify the hardness of NP? So this is the reason is that if you take the parity of the function f, even if f is in NP, but the whole function parity of times f is not likely to in NP, because we know NP is closed under AND operation and the OR operation, but it may not able to show that NP is closed under NOT. Okay, a more interested problem is like for some other language, can we show that some kind of hardness self-amplification? So it refers to starting from the function itself with a slightly loose hardness, then can we show the function is strongly hard, maybe on some other distributions? There has been intensive work working on this direction. For example, for optimization problems, by taking the function g to be the identity function and using the direct product lemma, it's possible to show that the hardness can be amplified to a very strong one. And some of the other works may not follow this kind of approach by taking the multiple samples. But instead, it may rely on the inherent structure of the problem itself. So the test we consider here is of evaluating integer value functions or approximating real value functions. And this definition can capture many natural problems that we consider in the complexity world. For example, the max click problem, which we want to output the max size of the click given a graph, and the max set for approximating the real value functions. It can capture the problems like approximate sharp P or shallow entropy. Before going through the how can we amplify the hardness, I'd like to define the closure property. So a function f is closed under G. There is this efficient way such that by taking t copies of x1 to xt, there is an efficient way to map it to a larger instance y, such that f of y is equals to g times f on the input x1 up to xt. So by some observation, we know all of the problems listed above seems to be close under the operation summation. Here is an example for the max click problem. So the inputs are 2 graphs. There are 2 subgraphs, and there is the goal is to output the max size of the click, and then there is an efficient way to construct a larger graph. So here, and such that the max click of the larger graph is equivalent to the summation of the max click of these 2 subgraphs, by just link all of the edges between the load sets. Okay, and now the goal of us is to show if f is y minus delta hard on some distribution, then the summation of f is delta prime hard, some small delta prime on the product distribution of D. So this statement, since if the function f is closed under the summation function, then we can claim that the function f is delta prime hat on some other distribution d hat, and the d hat can be generated as follows: like sample t copies from d and do the combination operation, and this step can be done efficiently. As the corollaries for the problem we mentioned about the max-clean, max-set, and approximation problems, we can show the Hardness self-amplification for this part of problems. Okay, so and then this is our one of the main theorem, which shows that for evaluating any integer value function that maps from n bits to a certain range, let's say m is polynomial in terms of n, then if assuming the evaluating the function is 0.9 hard for some circumcised s, then the summation function can amplify the hardness to like the order of m over square root of t. So intuitively, if m is some value in polynomial of n, and you take a sufficient large t to be is also some polynomial in terms of n, and this hardness finally mapped to an inverse polynomial, which is good. To give you a quick intuition about why the summation function can amplify the hardness, we would like to show this following lemma. We have a slightly stronger assumption on the hardness of the function itself. So assume the function there is a hardcore set H on which the function is half plus half epsilon hard, and then the summation can amplify the hardness to something like 1 over square root of t and plus square root of t times epsilon. So let's first try to understand what is the best parameter for the hardness of f that we could hope for. So if assuming the function f is with stronger hardness, that means like the function is balanced on the set H. That just means the probability that f equals to 1 is approximately the same as the probability f output 0. So then for this function, if you take this fx to be the Bernoulli distribution with the parameter half, and then fx is actually a binomial distribution, and the highest probability mass that f prime equals to the a certain value is something like t choose t over 2 divided by 2 to the t, and asymptotically it is 1 over square root of t. And if the epsilon is sufficiently small, then this whole term is dominated by 1 over square root of t. And so this statement is kind of optimal. And to prove this statement, we observe that assuming the strong hardness, it actually implies some kind of indistinguishability between the set H0 and H1. So this is the pre-integral set with respect to 0 and 1. Then we claim like for the algorithm, you cannot distinguish them with advantage more than epsilon. And then define some hybrid distributions hk to the t. This is the set of the inputs that there exist k numbers of the xi's that within the set h1. So the uniform distribution of hk to the t is equivalent to, say, I sample k numbers of xi's from h1, and the rest of them are sampled from the h0 and output a random permutation of them. So by some standard argument, it's possible to show that these two sets, hk plus 1 and hk, are also indistinguishable with the advantage bounded by epsilon. And then since we have this inequality, we are able to bound the hardness. So the probability that the algorithm can solve f prime, it's by expanding this probability, then so the first term is f prime equals to k, which is t choose k divided by 2 to the t. And for the remaining part, we would like to switch all of the probability condition to the same one, which is switch f prime equals to k to f prime equals to t over 2. And then about this probability, this condition probability can be bounded by here plus the gap between k and t over 2 and times this epsilon. And then because here, this is, we know that the summation of all of this probability equals to 1, and this is a converse combination of all of the t choose k, and then it can be bounded by the largest value, which is t choose t over 2. And the rest of the part is exactly equals to this value. And then we are able to show that f prime is 1 over square root of t plus square root of t times epsilon hardness. And then let's get back to our main theorem. The overview of the proof is shown as follows. So we're starting from the assumption that a function f is 0.9 Hardness on the uniform distribution. Then we would like to find a hardcore set on the which is a subset of the uniform distribution, and to show that f has a very strong hardness on the hardcore set. But this hardcore lemma is not the standard, the one which is the imperial hardcore lemma. From the second step, by the lemma I have shown before, it can we could obtain that the summation function can amplify the hardness to this ratio. And in the last step, okay, because of the hardcore set, there is no guarantee for the structure of the hardcore set H. For example, whether the hardcore set it can be efficiently generated. We would like to finally go back to the original distribution, which is the uniform distribution we start with, and to see if there is kind of strong hardness we can get. So the last step is quite natural because you think about if you sample t copies of xi's from the uniform distribution, and then the expected value of this instance that falls in the hardcore set, it's exactly the relative size of H times the number of times T. So which is approximately T times M to the -2. So here just replace this T by T times M to the -2. Okay, then it remains to see, to show the first part. Let me connect this with the imperial hardcore lemma, which states that if a function f is 1 minus delta hard some distribution, then there exists a hardcore set with relative size at least delta, such that f is very hard on this hardcore set. So for some intuition, the point we start with is, let's say, we first pick a circuit, and then there exists some of the inputs that the circuit cannot solve. But this lemma implies that actually we can change the step. So one of the proof for this is by the minimax theorem that is said if allow two players, one choose the circuit and one choose the set of input. If we allow them to use some mixed strategy, and it's possible to switch the order of the order of these two players. So that is you first pick a set, and then there is no algorithm can solve correctly on this set. But this lemma is not sufficient for the use here because we have an additional requirement, which is this f prime, the output of f on the hardcore set should be restricted within two values, let's say A and B. So to show this, we define some new problems with respect to f. Therefore, any pair of AB, let's define the relation, let's say IRAB for on the input x. For any input x, if fx is falls in the set A and B, then the only valid value is fx. And if fx is not in the set AB, so then no matter which answer the circuit give me, I don't care. I just take it as the correct answer. And then we able to claim that there must exist such kind of relations that with this hardness 1 minus delta over m choose to hard on the uniform distribution. And let me skip this proof of this. Okay. And then with this guarantee that a certain RAB is hard, you know, like only the potential hard input of RAB is only within the set F inverse A union with F inverse of B, which is the pre-image set. Then we can claim that F has this hardness the pre-image set. So by taking the hardcore lemma, we know we were able to find a hardcore set that is within the pre-image set of A union with pre-image set of B, on which F is strongly hard on them, and with relative size delta over m choose 2 times 2 to the n. So now both of the requirements can be satisfied. And we've almost complete the whole graph of this. Okay. So this is the statement that we were able to show, and by taking this epsilon to be 1 over t times m to the minus 2, then we can obtain this simplified one. And for approximating real value functions, the result is like the summation function can amplify the hardness to the order of square root of m over alpha times the square root of t. And there is some kind of loss of parameters here because we have to handle the approximation error. And as the corollaries for the problem, say the max set and max clip problem, starting from the 0.9 hardness, we are able to amplify the hardness to the order of n to the minus 0.49. Well, this n is the input side. And for all of the approximating problem with additive error tolerance, like a constant additive error tolerance, starting from 0.9 hardness, we are able to modify them into the n to the minus 0.24. So that's it. So thanks for your attention.